Good day, everyone, and welcome to our webcast today. Our webcast today is Transforming Nutrient Removal in Water Resource Recovery Facilities through Suboxic/Low DO Treatment. This webcast is part 3 and the final part of a 3-part series on this topic. While parts 1 and 2 are helpful background for today's webcast, they're by no means prerequisites. So if you weren't able to attend parts 1 and 2, no worries. Also, parts 1 and 2 are available for on-demand viewing on the WRRF website. So after today's webcast, if you'd like to go back and view those, you'll have the ability to do so. For part 3, we are calling part 3 of this series Transition of Pomona's Water Reclamation Plant to Suboxic Operations. My name is Jeff Moeller, and I'm a Director of Research Services at the Water Research Foundation. And I'll be serving as the moderator for today's webcast. Today's webcast will be about 90 minutes in length, and that will include some questions and answers and discussion at the very end. I'll briefly go over a few housekeeping items as well as the agenda before handing it off to our first presenter. So in terms of housekeeping, you can submit questions through the question box at any time. We'll do a Q&A at the very end after all the presentations are complete. But please keep your questions coming in throughout the webcast. Slides and a recording of the webcast will be available at WRRF.org. And you can download the slides now and access a link to the project webpage under the event resources at the bottom left of your screen. So those resources are available to you now. A certificate of completion will be automatically generated after the webcast. If you have any questions about that, you can contact Michelle Suazo at the email shown on your screen there. And then lastly, we'd encourage you to stay until the end to fill out a quick survey with your feedback on the webcast. So you should see the agenda on your screen now. After the welcome and housekeeping, our agenda is broken into 3 different sections. First, we have an overview of Los Angeles County Sanitation District's Pomona Water Reclamation Plant, or WRRP. And that will be presented by Michelle Young, lead technologist at Carollo Engineers. And then Michelle's going to hand it off to Tom Weiland, supervising engineer, Water Reclamation Plant section of LA County Sanitation District. And he's going to discuss the facility and process control upgrades at Pomona Water Reclamation Plant. And then Tom's going to hand it off to Phil Ackman, supervising engineer in the research section at LACSD. And Phil's going to discuss process transitions in performance at the Pomona Water Reclamation Plant. And then after the presentations, we'll have some time reserved at the very end for discussion and questions and answers. Here's our 3 presenters today, Michelle Young at Carollo, Tom Weiland at LACSD, as well as Phil Ackman at LACSD. So without further ado, I'm going to hand it off to Michelle Young, our first presenter. Welcome, Michelle.
Thanks, Jeff. I appreciate it. I want to start off by, first of all, thanking WRRF for sponsoring, helping us with this webcast. And I'm going to give a brief overview of the DOE project and specifically Pomona Water Reclamation Plant. As Jeff mentioned, this is webcast 3 of a series. The first webcast covered more of kind of the fundamentals, like what in terms of microbiological fundamentals, as well as giving an introduction to low DO and Suboxic operations. Webcast number 2 was more focused on the design aspects of designing a low DO plant or Suboxic plant. As part of webcast 3, what we're going to do with this webcast is actually go into the case study that was part of this Department of Energy project with the city of Pomona, with Pomona Water Reclamation Plant. I would be remiss if I didn't acknowledge all of the amazing contributors we had as part of this project. As you can see right here, it was really an awesome combination of not only consultants, we had utilities on board, academics, vendors, all coming together to try to better understand how to control plants that are going to be running low DO and Suboxic conditions. And again, this project was funded as part of the U.S. Department of Energy's EERE project. Focus, the Energy Efficiency and Renewable Energy Department. So let's transition to actually the star of the show today, which it would be Pomona. So to give a broader background, Pomona is part of the Los Angeles County Sanitation Districts, LACSD as we like to call them. LACSD is comprised of 24 independent special districts that serve approximately 5.5 million people within Los Angeles County. For perspective, they have 11 water resource reclamation facilities in that area. As for Pomona itself, Pomona is an interesting plant. It's been around since 1927, but was taken over by LACSD in 1966. It has a design capacity of 15 MGD, but generally operates around 9. It's actually a bit of a scalping plant for the downstream AK Warren facility. They are currently have been doing biological nutrient removal at the plant, specifically using a modified Lutzak, Ettinger, or an MLE process since 2004. The configuration is essentially primaries into aeration or into an activated sludge process, followed by secondary clarifiers. The aeration process itself is composed of an anoxic zone, a swing zone, and then 2 aeration zones. There are 3 aeration basins at the facility. Another interesting thing about it is that the plant has 8 gravity media filters that go that effluent from the clarifiers flow into, and then that effluent actually goes down to a chlorination contact basin where chloramination does occur. And chloramination is a theme you're going to hear during this presentation. In addition to that, the solids from Pomona actually flow downstream to AK Warren, so they do not have to do solids treatment at the plant. In terms of Pomona's, it's important, I think, whenever you're talking about low DO operations at any plant, to give kind of a perspective of where plants need to run in terms of regulatory compliance. And so as you can see on this particular slide, Pomona has regulations for ammonia, nitrate plus nitrite, and nitrite specifically. The most interesting part about this, obviously, is the ammonia limit. That's part of what we're trying to target with this project is nitrification. And that that ammonia limit varies throughout the year between 3 and 3.9 milligrams per liter, depending upon the time of year that it is. The way that compliance testing works at Pomona is that the Pomona basically takes a compliance sample at the beginning of the month. If they pass, then they pass compliance for the month. Otherwise, if they don't pass, then they go through a series of essentially other checks to make sure that their average is below the current ammonia limit for the month. It would also be remiss if we're talking about a DOE project not to actually talk about energy. And so right here, you see essentially how Pomona is using their energy before we started this project. You can see 70% of the energy used at the wastewater treatment facility was actually used for aeration purposes. And so there were a lot of drivers that Tom's going to be talking about in a second regarding why they wanted to be more energy efficient. And it seemed like a no-brainer to collaborate with the plant to improve this energy performance. Now, let's shift a little bit of gear here. I think a part of the motivations for what we did at Pomona certainly were motivated by what we wanted to do as part of the overall DOE project. As you can see on here, there were basically 2 fundamental kind of thrusts to this project. One is the scientific understanding, the fundamentals of what we do, and that was covered in webcast 1. And you can see right here that includes things like kinetics, microbial populations, understanding that, understanding greenhouse gas emissions as well. Now, as part of the second part of this project, where we were more focused on design and operational considerations, which is what webcasts 2 and 3 have been about, we were looking at kind of trying to understand how we would ultimately design these processes for more than just a small pilot, as the case may be potentially. So we looked at things like modeling parameters, minimum solids retention times, mixing, aeration control schemes, et cetera, things that we'll talk about today in this presentation. Just want to reiterate that Pomona was a lucky it was kismet for us to have Pomona on this project for a variety of reasons. including some that will be discussed today. The fact that they were looking at significant infrastructure upgrades at their facility. They needed to reduce energy consumption at the plant. It's the fact that we could kind of control capacity going to the plant was also a major motivator. So we could actually divert if we needed to any sort of load or flow. The regulatory limits were kind of typical for certain parts of the country, so that was beneficial. Another thing that was very important here was the fact that LACSD, for us, in order to be able to really understand how to model these plants in the future, we need to understand kinetics. And LACSD has an amazing extensive lab capable of doing kinetic measurements. And so that was really beneficial as part of the whole thing here. And certainly reuse needs are part of a consideration whenever you're performing any sort of, I think, wastewater treatment, especially in the West. So with that is my overview of Pomona. And now Tom's going to take over and discuss facility and process control upgrades at Pomona. Oh, sorry, Tom's going to take over. I hope I said Tom, not Bill. Sorry.
Thank you, Michelle. So as Michelle gave you a little background, our agency was just getting started on a project to upgrade the aeration blowers and controls at the Pomona Water Reclamation Plant. And this opportunity then to participate in this full-scale demonstration site for suboxic nitrogen removal for a Department of Energy project basically came available. And we looked at it, and it was a really good fit because it incorporated many of the elements that our research section had already looked at. And so we agreed to participate, and the project was selected. And I always say that's when reality set in, because what we realized is we had a lot of upgrades that needed to be made to prepare the plant for this demonstration project, and we didn't have much time. So in the next part, I'll discuss the required modifications we made to make this project a reality. And then in the last section, Phil Ackman will talk about, we'll present the data and the results and how we went about it. So because everyone always asks, I will name products we use, but I caution this is not an endorsement. In most cases, there are other manufacturers that make other suitable products that work fine. So our existing blowers were they're from 1950, they're 50 years old basically. And they're 3 dresser roots, OIB, single stage, integrally geared centrifugal blowers with inlet guide vanes. And they were sized really for a time with maximum nitrification. They were sized for 15 MGD. Our current capacity is more like 9 MGD or the flows. And they do not have variable diffuser vanes. And the capacity, maximum capacity is 14,000. They have a turn down to about 6,500 CFM. And the blower was typically operated on the high end at about 12,000 CFM. And the blowers really didn't have very limited automation, and they actually required an on-site operator to start them. And as Michelle showed in the first section, the plant really had space constraints. It's tucked behind, hills on the south and a railroad on the north. And so when we looked in the past at possible options to upgrade these blowers, we're somewhat limited by what we could do in this space. And at some point then, when the dual turbo blowers became available, we started looking at it again. But that's where this project came along. Okay, so the first thing we knew is we had to replace the blowers. So what we did is we purchased a turbo blower. It's a dual core from APG Neuros. It has great turn down. It's 2,600 to 17,200. And they were able to, as you can see in the photo here, there's some really tight constraints on the space. In fact, on the top of the turbo blower, we actually had to go in a little bit into the hatch space with the piping, come back down. But APG Neuros was able to work with us and come up with really a custom configuration that worked well for us. And these blowers obviously had automation, and so that was another benefit to the turbo blowers. Okay, we also had oversized basically piping and mostly valves that comes into play. So we were designed again at a time to maximize nitrification. And so, you sized it big, you minimized the head losses in the pipes. And so, the problem with that was, head losses were low, but at the minimum flows, this valve was going to basically be less than 20% or basically closed. And that was going to make, air control really hard, if not impossible. And then at the open end, it's an 80% open. Valve doesn't really have any control either. I'll show it better in the next slide. So the valves were clearly oversized, but the question was, do we need special valves? And after discussion with our project partners on the team here, we decided we could still use the standard AWWA butterfly valves. So we placed the valves with smaller valves, and then we sized them to operate between the 20 to 80% opening for the airflows. And what I'd like to show here is, if you look at the figure on the left, it's just a reminder, butterfly valves are nonlinear. And so that presents a control challenge. And as you can see here again in the figure, it's like below 20%, it's basically closed. And, but it's the actuator that determines the valve position. And Tom Jenkins probably, he's had the best explanation that I've seen. And I use this from some of his work. What he did is he looked at, he took a standard actuator that might have like a 3% position error. And if you look at, the repeatability or being off a little bit, it makes a pretty big difference on the flow, which at low DO, that becomes a big deal, when you're trying to have precise aeration control. And they also looked at what the difference was with, in this case, it was a Rexa actuator, but they looked at the difference if you had a much lower error, how tight that control could be. So we were convinced with that we could try the butterfly valve basically with a different actuator. So we actually, like I said, we stayed with the butterfly valve, the standard AWWA valve. Basically, we sized it to operate between the 20 to 80% opening. The actuator is a very precise, accurate, repeatable positional control. We actually used Rotorque, which was recommendation from Epigeneros, and we also switched the. We had flow tubes, which may have been fine, but we just wanted to make sure we had the response time that was needed to basically have really precise control. Okay, we also had the existing diffusers were 9-inch ceramics from Sanitation. And we really had too many. We knew that. Again, it was designed for a time when we were trying to maximize, nitrification. So we had a lot of diffusers. It was on the upper end of, I don't have it in there, but basically we're operating at an average loading per diffuser of about 4.4, and the minimum was about 2.2 because we never really went that low. And so we weren't originally going to switch the diffusers. We were going to keep the ceramics. But then we had some thought as we got into this that, well, what if we do want to use the swing zones, or what if we do want to do intermittent operation? And the ceramic, the disadvantage of the ceramic is if you don't have air going through it, it will fill with water, and then which can cause fouling, but also causes a problem when you start to put the air back in. You have to get rid of all that water. So, and this plant does have these power dips that will bring down the blower. So in any case, that was a consideration, and we thought, well, maybe we'll go to membranes. But the other thing I should point out here is this figure on the left is the efficiency curve from Sanitaire. And as you have with a lower airflow per diffuser, you actually improve your oxygen transfer efficiency. And again, we were up at about 4.4 for the average and 2.2 for the minimum. So we decided to go ahead with membranes, but it was really late in the game, and so we stayed with the Sanitaire because it was fast. Basically, didn't require piping changes, used the same holders, and our staff could actually make the swap, and we had the stock in hand. So that's why we went with that. There actually wasn't the standard oxygen transfer efficiencies very similar. So there wasn't a huge change. It's got a very similar profile basically to the ceramics. And we then went ahead and basically with biowind modeling, with assistance of Corel engineers, we kind of came up with what we thought the diffuser spacing should be, or what the density should be. And they came up with a reduction in the swing of 18%, grid B 13%. Grid B is really the first aerobic zone, and grid C being the second of 42. And we actually backed off on it a little bit because it was a huge change for operators and for us to go into it. In hindsight, we probably could have done that. And probably if we did it again, we'd actually reduce it a little bit more. So as Michelle mentioned, there are 3 aeration tanks. They're in an MLE configuration. Each tank has a small selector zone up front. The flow in this case is going from the right to the left. So there's a small selector zone. Then we have an anoxic zone. Okay, the return sludge goes back into the selector zone. So it's kind of a mixing zone, and it's kind of hard even to call it a selector zone because it's really small. And then there's the anoxic zone, which is where the mixed liquor recirculation or internal recirculation is returned. And that's at a rate of like 2.5 of the influent. And then we have a swing zone. Historically, we've always used the swing zone as an anoxic zone. And then we had the first aerobic zone. We had a DO probe up front in basically that first zone. And then there's a second aerobic zone, and we had a DO probe basically at the end of that. And our controls, again, this was the existing configuration. Controls were very basic. We basically have a header pipe that basically feeds tank 1, and it has a master control valve. And then there's a common header valve, master valve, if you will, that feeds tanks 2 and 3. And the header valves were, the operator could select the DO probe that would control the header valve basically for each one. They could be different DO probes. And then a DO probe also was used to control the inlet guide vanes. So that was it. That's all the control we had. So all of the valves on to the aerobic zones were actually just manual. So the operator would set it where they needed to for those peak ammonia loads, and it pretty much stayed there for the whole day. And they'd make adjustments as things happen, or special situations. But in general, those didn't change very much. So that worked okay for the peak loading periods. But really at night, what that meant is we over aerated, and DOs went pretty high. Okay, and what I kind of want to show here is the influent ammonia load. So what we saw at this facility was basically, it was really low in the morning, but about 6 a.m. it started to really ramp up, and it ramped up really pretty quick, and then came down fairly quick, and then there was a second little peak at night. And in the past, really, because of our slow controls, operators would set a DO set point, set it basically high, set it early. You always had to get ahead of it, was the thought, right? And because it took some time really for an increase in air to basically translate into a higher DO and bring down that ammonia concentration. So it, again, the timing was off, and that usually resulted in ammonia breakthrough at the plant. So this plant, as Michelle mentioned, uses chloramination for disinfection. So as you can imagine, at night, we had very little ammonia to none. And so for chloramination, we ended up having to add ammonia back, basically, at night. And because of the way the controls were set up, we're always adding some ammonia because we really didn't have very control of the ammonia. So that all influenced kind of how we wanted to set up this project. So again, we were lucky. Our research section had basically tested really all this equipment. And so we already had some experience at other plants with the equipment we were going to use, or with the type of sensors and probes. And so what we decided was, again, I'm not showing the selectors on front, but we decided we were going to put a nitrate probe in the anoxic zone, a DO probe in our swing zone, a DO probe and ammonia probe in that first aerobic zone. And we have it located somewhat in the center. And then a DO and ammonia probe in that second to that last aerobic zone. And that again was sort of in the center. And then we'd have a nitrate and total suspended solids analyzer at the end. And we set this up because we knew that locations, even though we had tested these, we had a pretty good idea where these worked the best. We knew that we'd probably move them around a little bit. So we made sure that we had additional I/O, that we basically had extra length in the cable, so we had some slack so that we could change the placement if needed. So our research had section, again, it tested various sensors, and in this case, they tested some different ammonia sensors. And although there were many pros and cons, the selected sensor had really good repeatability at low concentrations, was fairly easy to calibrate, and was self-cleaning with minimal maintenance. And I need to point out, though, really that we had tested this in an aerobic zone, so it had good mixing, right? So going back to, before we settled on the location, one of the things we did is we did look at other locations because we weren't sure if we wanted to have an early detection or, say, a feed-forward ammonia signal. And so the instrument readings in these zones, so we tested it basically in the primary effluent channel selector zone and anoxic zone. And they seem to really underreport the ammonia peaks. And we kind of think that, it probably was due to some fouling. And again, we hadn't tested these in the location with mixing. So, I think we definitely found that mixing was important. That placement did show us, though, that we had some unbalanced primary effluent conditions. So the ammonia loading for the 3 tanks was different. So that did help us actually try to balance that more. And we did get it balanced and it eventually better. But really, once we started implementing the DON master control system, what we found is we didn't really need that early detection. And so we ended up putting the ammonia sensors only in the aerobic zones where we had good mixing, and which is where we had originally tested them. and they have been shown to have really good repeatability at those low DO levels. Okay, our DO probes, we use the Hawk LDO, and really the only reason is we already had standardized on that make and model at the plant, so we were familiar with it. It's what we had already. The DO probes are factory calibrated, have no membrane, don't use electrolyte solution, and we didn't use, actually, they do have a self-cleaning option. We don't have that. We actually perform a weekly PM. So our E&I staff goes and wipes the lens once a week. And, ultimately we used ABAC. And so with ABAC, ammonia-based aeration control, the DO really isn't as important as the ammonia sensor. And so, again, we started early controlling with DO. We had some, as we went into it, and Phil will explain a little bit more, but as we started using it, we also had construction projects at the site where we did some hydraulic shutdowns. After those hydraulic shutdowns, it seemed like a couple of the DO probes probably got a little fouled, and that made control pretty hard. And again, ultimately we went with ABAC, which again, in an ABAC situation, DO probes aren't as important. If you're going to use DO control, I caution, verify the accuracy and repeatability meets your process needs, and make sure you're doing the PMs that are required, or that's where I'd really recommend a self-cleaning feature if you're going to use it, specifically DO control, not ABAC. So for the nitrate probes, we went with the Hawk Nitrotax, and again, the biggest reason was it already, we had a SC1000 controller, and you could put 6 probes into it, so that just made the layout and the cost of the installation less, because we could use the same controller. And we placed the nitro probe basically in the noxic zone, and then one at the end, as I said. And we did not actually use this for the control. So it was good information to have. We could see what was going on. And so we also actually had looked at modeling at one time too with BioWin, and we saw that we have a pretty low mixed liquor recirculation rate. And really, we didn't see much benefit to changing those numbers. It didn't impact nitrates that much, so it wasn't all that. There wasn't much benefit to try and incorporate that into the controls. We also have we also installed some, and again, we used Hawk. We installed some total solids, suspended solids meters. We put one immersion type in each aeration tank at the end. And we also put one inline type in our ROS pipeline, which is where we waste from. And with that, we were able then to basically implement SRT control with Extra and Associates program. And what we wanted to make sure is we could maintain the same SRT as we transitioned to low DO. We maintained it at a total SRT of 9 days, which is for us 6.5 days of aerobic SRT. And we wanted to make sure we had a stable process, that we knew what was going on, and we wanted to take that uncertainty out of it. I do recommend, what we have is a wiper on it. With the wiper, these are kind of hands off, to be honest. So the benefit of the SRT was we saw we had a construction, again, we had construction projects that required some hydraulic shutdowns and some loss of plant solids. The SRT controller brought those back really quick. Okay. So the new instruments landed in an IO rack that was basic at the end of each tank. The IO rack communicates directly with the APG Neuros master control panel. There's a industrial computer installed inside of the master control panel, and it basically, all the instruments from the IO rack go into that industrial computer, processes a lot of data, and then basically provides DO airflow valve position blower set points to the PLC, basically, in our SCADA system. We did need remote access for star tuning and then also for real-time data access. And for obvious reasons, I'm not going to go into exactly how that was done, but just caution you that you need to consider some cybersecurity. You want to safeguard it, basically. Okay. Sorry. We also, this plant also has a secondary effluent ammonia analyzer. It's a wet method. It's ChemScan. We use it really for the chloramination. It lags by a few hours, but it was a really useful check on the ammonia probes. And so in general, it ran a little lower than the probes. I'm not sure if that was because there was some nitrification happening yet in the mixed liquor channel where we aerate, or if it just ran a little higher, but it was always very consistent. So what it showed is that those analyzers were very consistent, could be relied on, and we knew always where the secondary effluent was going to be, and ultimately the operators got pretty comfortable with this. We also installed at this facility sludge blanket indicators. Again, we didn't take it directly into the controls, but it gave us a real good picture of what was darnally going on in the tanks. And early on, we saw our turbidities increasing late in the day as we started to transition to low DO. And what became obvious was that as the sludge blanket was increasing is where our turbidity was spiking. We had plenty of filters, so that wasn't really an issue, but what it did is the staff was getting ready to leave for the day, and invariably we'd get this higher turbidity that would require filter backwashes, and they'd have to stay. So with this data, we were actually able to point out that we should increase the return activated sludge, bring down those blankets. So again, it wasn't incorporated in the controls, but it was useful. The total cost for the construction was $3.6 million. So as far as design and construction, as I said at the very beginning, we had a pretty tight time frame. We actually signed the sub-agreement for the DOE project in January of 2022. Basically, the design was by LACSD and the DOE project partners. Fortunately, we already had the procurement of the blower in the works. We had a lot of the, we knew what we wanted from the research field testing, and in some cases because it had a common controller. And construction, though, we really didn't have time for a standard public bidding approach. So what we had just as an agency started doing was using job order contracts for smaller projects. And that became basically a good way to get this work done in a short period of time. Okay, the existing controls, again, very, very basic. Basically, again, just two master controls on the header and the blower, and was one of the DO probes controls the header. Another one might be used to control the blower, but that's really as simple as it was. Okay, the new control system is basically, we have this instrumentation this one's going from left to right, but basically we have a DO meter in the swing zone. We have one also in grid A, grid B, the aerobic zones. We also have ammonia meter in the aerobic and one in grid B. So what would happen is the ammonia would go to this ABAC controller, and then it would basically feed set points for airflow, for DO airflow valve position, and then ultimately the blower flow also. So this was really, I encourage you to go back to the previous workshop where this was discussed in more detail. What I do want to point out here, though, is that the ammonia MPC basically uses a machine learning algorithm to basically set the DO target. And then there's a separate machine learning algorithm that basically sets an airflow, and another one that basically takes that airflow to valve position. And so if you think about it, it's like the machine learning is really learning from what we're doing. And so it was really important that you have tight control, and that when you move the valve, you get pretty precise each time what you were trying to get. Okay, and so early on, we looked at comparing the basically PID with what we were getting with machine learning or the DON master from Exeter and Associates. And as you can see, we got really tight control with the machine learning program. And again, this was discussed in more detail in the last workshop, so I encourage you to go back and review that if you haven't seen it yet. But we did use a basic and SRT controller by Exeter and Associates, and really it's been shown to, it's quite a bit more accurate than trying to do manual control. Okay, early on, one of the things we wanted to make sure we did is we set up our boundary conditions. Basically, this was what the operators were concerned about. So so it's like we went and said, hey, what's your minimum? How low do you want to really go? Well, in this case, it was driven by the fouling or that might be happening at 0.5, right? But at the max, it was like, how high do you feel comfortable going? And so we used basically their past experience to set up this criteria. And it was a real trust factor with the operators, because they knew that, we set up ahead of time what they were willing to maybe deal with. And one of the things, like I said, is this turbidity of 10. It's like, they didn't really want to see it go higher than that. And so we did work on keeping those things down. So with time, though, the operators got a lot more comfortable, and then we actually softened these up or loosened them up a little bit, if you will. So you may ask the question, how do you exert pressure on the biomass for adaptation to a low DO operation while still meeting discharge requirements? And Phil's going to go into this a lot more, but some of the things I want to point out here is, we knew the instrumentation was very reliable. We knew where we were each day and could intervene if we needed to. And that is specifically true with ammonia, which was really one of our key measures. But we had all this other information about blankets and turbidity. Okay, our initial approach was really, let's just try to keep the DOs and all the aerobic zones the same, and let's start to bring it down together, wait 2 to 3 SRTs, lower it again. And that worked initially, but as we got lower, we found basically that we'd have these occasional ammonia breakthroughs. And some of that was also because we had these construction impacts. We had a project that required us to basically do hydraulic plant shutdowns for, up to like 8 hours. And we had a number of these. And when we did this, we tended to lose a little biomass. And of course, you lose the biomass and nitrification, all of a sudden is not there. And so we were dealing with that. So ultimately, we ended up using ABAC, and we ended up placing basically this upper and lower guardrail, if you will. And really what that means is you let ABAC determine what the DO needs to be, but you let it go up to a max. And again, we brought that down over time, and then also with a minimum. So even though ABAC might say, it could go, say, to 0.4, we were going to constrain it at maybe 0.6 or 0.65. And again, at the high end, Even if it wanted 2.5, we were constraining it at 2 when we started, right? And we brought that down. What we saw, though, is that with the diurnal peak, we were still getting these occasional, basically breakthroughs. The composite for the day was fine. We never had an issue with the composite being in compliance. But what we found is that, yeah, we had this ammonia breakthrough, and the way we modified the approach was for a number of hours each day during that peak ammonia loading, we just let that guardrail go higher temporarily and then brought it back down. So with that, I am going to turn this over to Phil, who's going to present the data.
Thanks, Tom. So as you pointed out, we're using ammonia-based aeration control. So it's extremely important to have ammonia sensors that are well calibrated and that you can rely on. So I just want to spend a couple of minutes on what procedure we use to keep those ammonia instruments calibrated. So the procedure that seemed to work really well for us was to take samples. We took grab samples every 2 weeks, and we would take 2 samples at each sensor location. One would be a sample at a higher ammonia level and one at a lower level. And here you see a comparison of the lab samples versus the sensor samples. We have a pretty good distribution of some are reading high, some are reading low, but there's no real overall trend. And it's plus or minus about 1 milligram per liter. So this is probably about the best you can do. And and the nice thing about the Hariba instrument is that you can put a calibration, you can put a linear calibration into the controller. And so as the instruments drift, you don't necessarily have to recalibrate. Here we see we're looking at the current and past values to see whether or not the calibration coefficient we're using is still working out for us. And there is some interest in ISC sensors to see whether or not they're reading well at low levels. And the nice thing about the Haribas is we were getting very good linearity at low levels. You could see it well below 2. The instrument still pretty solid readings. And next, what we don't want to do is we don't want to overreact. I've seen some thoughts in the industry that you should set a fixed percentage of error or a fixed offset of so many milligrams per liter off, and then you should recalibrate the instrument. But we really wanted to use our judgment, not set some fixed boundaries. You see here, there are many times, there are a couple of times here when the error rate was fairly high. And we have to keep in mind that there's a big difference between a 20% error rate at 1 milligram per liter and a 20% error rate at 10 milligrams per liter. So as we can see here, we didn't overreact to these higher percentages. And subsequent sampling did not bear out that error was really there. So again, we wanted to use at least several of our sampling campaigns before we made a decision. And here we also see the value of doing 2 samples. If you look at the May sample on the far left-hand side, we have one sample that's a 0.5 milligram per liter off, but another one that's 3.5 milligrams per liter off. So they both probably can't be right. So if we react to the 3.5 and make some sort of adjustment, we'd see that the subsequent sampling event showed that was just an outlier and that we really didn't need to take any action. And we see throughout July and August here that the instrument's reading a little bit high. And again, we're usually taking data from at least 3 sampling events to inform a decision as to when to change the correction factor. And in this case, we had enough data to make that change. And in general, with ammonia-based aeration control, you could tolerate being a milligram per liter or so off. If it's in the mid, the end zone will compensate. And generally, if one is reading a milligram per liter high, you'll probably have another sensor that's reading a milligram per liter low, and they sort of cancel each other out. So this is similar to what Tom showed. This is some actual lab sampling that we did in support of biowind modeling. And I want to call your attention to the time period between 8 a.m. and 4 p.m. And that's when that ammonia load really increases. At peak, it's almost double what it is before the increase. And so this presents sort of an interesting problem and maybe limits in some way what we can do as far as transitioning to low DO. We'd like to push the DOs down lower, but we have to provide enough air and DO during these peak periods to allow us to meet our regulatory requirements. So as you'll see in the presentation, this became kind of a limiting factor, as well as we were able to use this to really chart our performance. So as Tom pointed out, before we completed the modifications and we put the individual valves in, we had a DO that looked somewhat like this. Our DO was always very high in the middle zone and not very well controlled. And in the end zone, there are many times when the DO was very low and not very well controlled either. So one of the really interesting things about putting the ammonia sensors in was that we could see, this isn't right. Got it. Okay, so it looks like there's a slide missing, but we did have an imbalance in the ammonia in the tanks, and we were able to use the ammonia sensors to identify this problem, even though we only have 3 aeration units, and the channel feeding them is not very long. We were able to use the ammonia instruments to better, the operators were able to make some valve changes and improve the distribution of the ammonia. And in the beginning of the project, we started off with simple vanilla DO control. And here you see again during this time period from 8 o'clock to 4 o'clock that we're using a much higher DO set point in order to provide adequate nitrification during the period of time in which we have increased ammonia loads. And as we transition to ABAC control, as Tom was talking about the guardrails, you can see here during the 4 to 8 period that we've set a consistent DO that's different in each zone. And during those off-peak times, the DO is varying to maintain a ammonia set point. And what we wanted to do was that we felt if we let the ABAC control completely define the DO point, that it would allow the DO to go too high, and that would make the average overall daily DO not low enough and not create enough pressure to acclimate the sludge. So we sort of wanted to hit a happy medium to where we have a DO that we're not getting too much ammonia breakthrough, but we're getting enough nitrification so that we can meet our regulatory requirements. So here, a little sneak preview of some of the results from later on in the project. Here we see under ABAC control, the DOs from each zone are much lower, and we're also meeting our ammonia set point of about 1.5, which is what we needed for chloramination, which allowed us to no longer need to add additional ammonia. So as Tom presented sort of an idealized, what we called the high and low guardrails for ABAC control. So here we see what the actual guardrails were that we used during the project. As we started off the project, we had relatively high maximum DO guardrails, and this is for the middle aeration zone. We started off at 3, and we were able to transition fairly quickly in a couple of months to about 1.5, and then it took another additional 3 months or so to transition that high guardrail to a lower DO of about 1, at which point we set a maximum DO that was different for the peak period as for the rest of the day. In the beginning of the project, the minimum DO was really set as almost a fail-safe. If the ABAC controls were not working properly, then we had a DO level that we thought was predictive of treatment performance. And later on, as we gained confidence with the ABAC control, that minimum DO became more associated with the minimum amount of mixing required. So here we see the similar high and low guardrails for the end zone. And in the end zone, we actually started out with really low DOs in that zone, as that's the way that zone was typically operated during that period of time. And so we had a situation in which the mid zone is working as hard as it really can, and the end zone is just slacking off and really adding nothing to it. So we actually had to increase the DO, maximum DO that we allowed in that end zone to the point where both zones were fairly equal and were contributing about the same amount of nitrification before we could start to reduce those maximums. So now we could take a look at some of the performance. As Tom pointed out, we were really able to use the ammonia sensors in the secondary and at the end of each tank to really monitor performance as we changed DOs. And we could very clearly see when our nitrification rates were improving, when they were staying about the same, and when they were deteriorating. So here's the beginning of our transition to low DO, where we're going from a DO of 2 to 1.75 to 1.5, and we really don't see any significant difference in the peak ammonia that we're getting out of the plant, which appears to indicate that those DOs were probably excessive and weren't really adding anything to the operation. Near the end of March, you see a period of several days in a row where the peak ammonia out is decreased. And those are the signals that we use to identify a point at which we could decrease the DO set point again. As we did at the end, at the beginning of April, we were able to go down to 1.3. Now, although this project took about a year for us to transition from high DO to low DO, there were many times in which the performance wasn't changing very much at all. But there were also times in which the performance would change fairly dramatically over a fairly short period of time. Here we see over a period of about a week, we'd gone from an effluent ammonia of about 9 all the way down to something approximating 3. And so we're not really sure what's going on here. Maybe the sludge is acclimating over a long period of time. It has to reach some tipping point until you see a process improvement, or perhaps the conventional wisdom of needing 2 to 3 SRTs to acclimate is not always the case. As you might have noticed in the guardrail slide, there were hiccups along the way, as every project. Not everything went entirely smoothly. And there was a time here in which we had to go back to slightly higher DOs. I'll talk a little bit about that. On the left hand of the slide, we see we're operating at a maximum DO during that peak period of 1.3. And the two numbers there are the mid zone and the end zone. And as a result of a shutdown that occurred to support the construction project, after we started the plant back up, we noticed that the nitrification levels were clearly very different than they were before the plant shut down. And so our response to this was to increase the maximum DO levels immediately to see if we could get back to the nitrification levels we had. And it took us about 5 days to get back to the effluent ammonia levels that we had before the plant shut down. And then we were able to slowly, over time, reduce that maximum DO guardrail and ultimately get back to even lower than we were when we started. And it took us about 3 weeks to do that. And the interesting take-home point here is that when we did have events, of which several occurred during the project, that where we didn't have the nitrification rates that we previously had, we were able to increase DOs to offset that. And we were also concerned that running at the higher DOs for several weeks may set the project back, that we're going to lose the acclimation of the activated sludge to, and that we were basically going to have to start all over again. But what we did notice is that in fact did not happen, that we were able to get back to fairly low DOs fairly quickly, and it didn't have any residual impact. So again, there were times in which we noticed fairly dramatic changes over short period of times. Here at the end of August, we're running average DOs of under 1, and our effluents were about 4.0, which is pretty good historically for the plant. And all of a sudden, those peak ammonia just simply disappeared. And we had performance that we had never seen before, where we don't have those peak ammonia events occurring. So another way of looking at the plant performance is, instead of the ammonia, the effluent ammonia, to look at the average DOs. And this is a chart showing the average DOs for all the zones throughout the project. And in the beginning of the project, in 2023, we had, of course, very high DOs. And at that point, we're running under DO control. And we're lowering the DOs to more reasonable rates. When it took us about 3 months to lower it to 2.0. And thereafter, it took about another 3 months to lower it from an average of 2.0 to about 1.5. And then about 6 months to go from 1.5 to about 1.0. And during this last summer, we were able to push the average DO below 1.0. And you can see during the last several months of the summer that our performance was fairly consistent, and we were hoping to push the DO below even where we were at. Our lowest average DO was about 0.75, and we were hoping to push it even lower, but that didn't seem to happen. We seemed to sort of hit a level of performance that was just a baseline, and we couldn't move any lower. And here's another view showing kind of the same thing with the DO, adding the effluent ammonia in it. And again, you can see in 2023, we were fully nitrifying. We were not at ABAC control. And when we went to ABAC control, you can see some of as we lowered the DO, we allowed more ammonia in the effluent. And with time, those effluent numbers decreased, and that allows us to make another step change in the maximum DO. So as engineers, we like to twiddle knobs, and we were unhappy with the fact that although our performance in the summer was very good and very consistent, we didn't seem to be able to push the DO down any lower. And so what we came up with is the idea of, since our effluent ammonia numbers were so good, that we could actually allow the ammonia set points to drift up a little bit. And since we're under ammonia-based aeration control, allowing the ammonia set points to come up should mean that the actual average DOs should go down. So we implemented 2 step changes in the ammonia set points in an effort to see whether we could drive the average ammonia lower than what we were at. Unfortunately, this didn't make a very big change. We think what had happened is during the fall, our effluent temperatures, or influent temperatures also, are starting to decrease. And as they're starting to decrease, that decrease caused a little bit of change in nitrification, and that change in nitrification offset any improvements we got with respect to the increase of ammonia set point. So another way of looking at performance, instead of the average DO of all the zones, here we see a frequency plot where we're looking at the DO throughout the day and the percentages. And for the mid zone, our median DOs during September and October were a little less than 0.75. And you can see that our performance during that time was pretty consistent, not a lot of variation. Similarly, for the end zone, our median DOs were a little bit less than 0.7, with again, very consistent performance over September and October. So here we have a chart showing DO frequencies and comparing it to some other plants that are doing low DO. And some of those plants are doing a little bit better than we are with respect to operating at really low DOs of under 0.5, a higher percentage of time. But we're the only MLE plant represented. And so we don't think we're really doing too bad. And as Tom sort of mentioned, in some manner, I think our low limitations in DO are defined by the number of diffusers. And we had to sort of guess how many diffusers we wanted to remove. And it turns out that we probably could have removed some more diffusers, and that would have allowed us to go to a little bit lower DOs than we're currently limited at Q. One of the things we're concerned about in the project is filaments that might be growing in low DO environments. And here we see sort of a historical plot of about 6 years worth of data for SBIs at Pomona. And you do see time periods in which the SBIs are 200 and above. And there does appear to be a seasonal variability to this. And here's what the SBIs look like during the project. And you can see during early 2024, as we're transitioning to lower DOs, we did see an increase in SBIs from about 100 to over 200. And we did have some concern that these high SBIs may be caused by the low DO environment. But as luck would have it, later on in the summer, those SBIs dropped off again back to 100, giving us some indication that perhaps it's not low DO after all. This was just the seasonal variation that we'd seen previously. During this time period where we had high SBIs, we did do a lot of microscopic evaluation. And you see on the left here, the flocks that are high SBI flocks, where we see a lot of filaments outside the flock, which is indicative of higher SBIs, compared to the micrograph on the right, which is the lower SBIs. And we did try to identify the filaments, but it did appear that over time, the predominant filaments changed, and there was never really one filament that stayed predominant through the entire time. Again, maybe giving some credence to the fact that it wasn't necessarily the low DO that was causing the high SBIs. So, of course, one of the important benefits of running a low DO is a reduction in energy costs. And we see here on the far left-hand side, the energy use that we had when we were using the old process air compressors was about 1,300. And there was a pretty significant change as we installed the turbo blowers. And even though at that time our DOs were fairly high, we still saw a pretty significant benefit. And as we slowly reduced the DOs at the end of 2023, you saw the electrical use decrease. And as we started to transition to low DO and got into fairly low DOs of under 1 at the end of this summer, you see that we hit a low of about 400 kilowatts per MGD to flow. Now, at this facility, we use air to mix channels. So for this particular slide, I have removed the channel aeration air, and I'm only referring to the air that's being produced by the process air compressors that goes to activated sludge aeration. So here are some of the effluent results throughout the project. In the beginning of the project, we had a TIN of about 8. And during that period of time, again, we were almost fully nitrifying. And now in 2024, where we're under ABAC control, we have about 1.5 parts of ammonia that we're allowing to go out of the system. So if you add that back into the TIN, you can see that our TIN performance really throughout the project has been pretty consistent, and there are no real significant changes at all. And this is sort of an interesting slide. As Tom pointed out, we have a mixing zone. We wouldn't even want to call it an anaerobic zone. It's a very short zone. And despite that, for an MLE plant, we did fairly good phosphorus removal. In the beginning of the project, our influence is probably about 5. And you see the effluent numbers of somewhere between 0.2 and 0.6, 0.8, which is surprising for an MLE facility. And near the end of the project, during the summer, from June to October, when we're at DOs, average DOs that are well below 1, you see the phosphorus performance stabilize a little bit to pretty low values of 0.2, which again is quite surprising for an MLE plant. So I talked a little bit about the acclimation of the activated sludge to low DOs. So what exactly might be happening here? What is going on in the activated sludge? And I think that the current theory is that there are some kinetic changes in the activated sludge. And I have here just some monad curves that look at the low DO, the KDO, which is the DO at which we have 50% nitrification rates. And here I have a maximum nitrification rate of 4, which is pretty similar to what Pomona is doing. And as we see the K value change, that DO that's required for 50% nitrification starts to be reduced dramatically, meaning that at lower K values, you get a lot more nitrification at a lower DO. So we did a number of kinetic tests throughout the project, and we see here at higher DOs, at DOs above 1, we have a significantly higher KDO. But as we decrease the DO, we did see a difference between high and low DO. But as the DO of 1 and a DO between 0.8 and 1 and a DO of 0.8, we really didn't see a significant difference between the KDOs. HRSD has a lot of data on this, and they did a far more extensive work than we did, but our data is somewhat consistent with theirs with respect to the fact that the sludge does acclimate to low DO, and that KDO does change as that acclimation occurs. So in conclusion, we were able to transition the plant to low DO operation. It did take a long time. It did take about a year. We were able to maintain the SRT pretty consistently throughout the project. We obviously got pretty significant cost savings in electrical use, mostly from going to more modern blowers, but also there was some significant savings in going to lower DO operation. And we have a lot of N2O data that we're still evaluating. We haven't had an opportunity to go through all that data yet. So we're not really sure what the impact on N2O of the lower DO operation is. So at this point, I'll open it up to questions. Turn it over to Jeff.
Thank you, Phil. I really appreciate that presentation. And this time, we'll have our Q&A session. So we got a number of questions that have come in during our first 3 presentations. And we ask you to keep those questions coming in. We've got about 15 minutes left in the webcast today. So we'll spend the last 15 minutes doing some Q&A. And would ask the other presenters to turn your cameras on and join us. We'll have a little panel, if we will. So I'll start out with one question that came in kind of early in the webcast. And the participant asked, did the reduction in energy use adjust or change the blower technology selected?
I guess I'll answer that. So I would say no. I mean, from the beginning, we were looking at, really what I should have mentioned in my part of the talk was the turbo blower we selected had the range that we needed. That was the only blower that we used. And there was another question someone asked that kind of was similar. So, you know, we went into it. We did find out as we went low, because we had a tank out of service for construction, that we could have actually gone lower with the blower that we did select for that case where we have a unit out. And, you know, what we had to do temporarily was blow off some air just to be able to get a little lower to keep at times, not for a great portion of the day, but at those times when we were getting really low.
Thank you, Tom. We had another question come in. They ask, how do you see if machine learning is a good or not so good fit in process control at water resource recovery facilities when the plant is running at suboxic/low DO treatment mode? Any thoughts on the pros and cons there?
I'll start and then maybe
Tom.
you can add, Michelle. But so this was my first experience seeing machine learning applied within a wastewater treatment plant. And what was interesting is, you know, something like, again, we had 3 different machine learning libraries. So where you went from flow to valve position, that's a mechanical process, very, you know, there's machine libraries that cover that type of situation very well. And again, as long as you get back to that real precise position on the valve, it works really well. And then the other ones, you know, you kind of look and go, well, that's biological. You know, it's like you're going from ammonia to what the DO set point normally needs to be. Surprisingly worked very well. I was surprised about that. And the other, talk about a little bit pros and cons. One of the things to keep in mind, though, is because it's machine learning, if it's running and something's changed, so like when we had these construction impacts, you'd bring in some pretty different data. It would take just a little bit of time for it to basically get that bad data, if you will, out of the system, because it was learning that, right? So what we had to do there is be careful as we started things back up, that with our constraints, mins and maxes, we stayed where we needed to be.
The only thing I would add is there are probably other ways to do it. I think the most important thing is that you're able to hit your set points. If you're able to do that, then your control is going to work. It's going to be good enough.
And more importantly, consistently, I think, around your set points. Because if you have I think in our particular situation, being able to consistently hit the set points allowed for better biomass acclimation. They were just spending more time around some of those low points versus the high points and things like that. So I think all in all, certainly it helps. I think the jury's still out as to, you know, some of the nuances of it, like how often do you need to be adjusting the DO set point? I mean, the valve position to meet the DO set point and things like that. So certainly stay tuned.
Thank you. We had another question come in that asks, other than the guardrails noted, was your airflow determined directly from ammonia measurements, or did you use DO as an intermediate parameter?
Well, we didn't show
there was an ammonia set point, which again, there was a machine learning library that then said, based on this ammonia set point, this is at this time of day, or you know, this is what the DO set point needed to be. And then there was another machine learning library that basically said at this DO set point, the flow needed to be this, right? And then there was a third machine learning library that basically said at this flow, the valve needed to be this. So that's how the one we're using kind of works. There's obviously other programs out there, but with the machine learning, that's how it worked.
we kept the same set points through a lot of the project. Only at the end were we kind of changing them to try to force the DO to be a little lower.
Yeah, and I guess maybe what we should talk about a little bit is, again, because it's chloramination, we're adding back aqueous ammonia for that disinfection. What we started to see a very consistent, very ammonia, where it stayed basically, we hit a target when we raised it a little bit. And really, we looked at how much could we reduce the addition of ammonia by keeping it a little higher. So that was another kind of goal we had as we were getting towards the end here of the summer.
I think, overall, if I can interject here real quick, what I thought was interesting with it is certainly we could nitrify consistently at lower and lower DO set points. I think the fact that BioP was consistent, so the effluent phosphorus was pretty low. And I just look at this from a Colorado standpoint, because we're looking at limits with Reg 31 at 0.17. They're averaging a 0.2. I mean, that's pretty bloody good. Maybe a little above that, a 0.23. But more importantly, we got this interesting bonus kind of learning out of this, that you can pretty well manage those ammonias to whatever chloramination level you need. And kind of almost, I hesitate to say eliminate, but certainly significantly reduce the amount of ammonia you would need to add back into the system. So that sort of control is a huge commodities blend as well.
Very good, thank you. We had another question come in that asks, what were the SRT and the wastewater temperature during the study period?
I think our lowest wastewater temperatures probably were like 23, 24, and our highest are probably 29 C. I mean, in Southern California, we don't get too cold, and probably near September is when the highest temperatures are.
Yeah, in September, the effluent was 86 degrees Fahrenheit.
Yeah.
And then the SRT that we maintained during the transition to low DO was a total of 9, or an aerobic SRT of 6.5 days.
I think we went as high as 10, but not much higher than that, if I recall.
Correct. We started off a little higher.
Thank you. We had another participant ask, what are the historical average influent TKN concentrations at Pomona's water resource recovery facility?
So our average ammonia is typically in the high 30s, 38 to 39, somewhere in there. TKN's about 1.5, so TKN's probably about 50 something. And the nature of Pomona is, because it's a small plant, it doesn't vary. The loads do not vary much from day to day. So kind of what I didn't say is some of those reductions in effluent ammonia, you might say, well, maybe they were changes in influent. They weren't, because our influent is so consistent. We could use the ammonia sensors to determine when our nitrification was improving.
Thank you. And we had another participant ask, what are your thoughts on the reasons for the good effluent phosphorus levels? Could it be anaerobic operations that occurred in the anoxic zone?
We've actually seen this in our other plants as well. Our step feed plants, and we only have a couple MLE plants, but we've seen phosphorus removal with not a lot of anaerobic zone, and as with our step feed plants, we have a selector zone that's much larger. So I don't know. I guess the phosphorus removal in our MLE plants is a little surprising, maybe not so surprising in our step feed plants, where the selector zone is much larger. We just have good bugs.
Thank you. Another participant asked, how low was the airflow to keep the last aeration zone fully mixed? And what was the DO in this basin?
So I can tell you what we ended up doing. We changed the boundary condition in the first aerobic zone to go as low as 325 CFM. And the DO associated with that, we let it go to 0.3. It did at times, but very short period of time, go that low. And then for the last aerobic grid, we let that go to 125 CFM. And we let that DO go to 0.2. It never really went much lower than 0.3 though. And we really were watching this to see what the mixing was. And the operators felt we still had decent mixing at those lower numbers, which is why we changed that boundary condition.
And that put us, I think, well below 0.5 CFM per diffuser too. Yeah. Which again, maybe, we could have removed more.
750 would have been, 750 and 250 would have been 0.5. And we let it go to 325 and 125, so about 0.25.
Thank you. We had another question come in from our viewer who asks, what makes plant owners, still resistant to low oxygen treatment, in your opinion? And I know this is kind of, curious your thoughts.
I think it's an uncomfortable place for an operator to operate. Their license is the one that's on the line. And so until you can prove without a doubt that you have the redundancy in the system and you can meet the requirements, I think it's a hard pill to swallow. And that's why setting those boundary conditions is so important when you start this. And then as you go through the process, you iterate on those boundary conditions again to see if that's the right place to be. That's just my personal opinion. I don't know, Tom, Phil.
Well, you hopefully see in the presentation, though, it's a pretty significant effort. And I probably wouldn't want to do it without the proper instrumentation. Having the ammonia instrumentation was just key in allowing you to figure out exactly where you were at any given time and allow you to make the type of adjustments. And not only that, if you made an adjustment that went the wrong way, you could very quickly see that and make a correction. So we didn't show any of those slides, but I assure you that there were some of those events.
Thank you. I think we've got time for maybe just one or two more questions. We had one participant ask, how often do you need to calibrate your ammonia, nitrate, and DO sensors?
Well, we were taking lab samples every 2 weeks, but we probably weren't changing the calibration factors more frequently than every several months. It wasn't consistent. There may be some instruments that would go 4, 5, 6 months without needing any change, and another one that might change every 6 to 8 weeks. So it very much depended on the instruments, and we felt like having the lab samples every 2 weeks gave us enough data to watch that.
Thank you, and maybe we'll make this the last question. Are there any future improvements being considered at this point in time?
Well, we have 11 water reclamation plants, and so let me answer it a different way, which is we really want to take this project, apply what we learned to our other facilities, because the energy reduction was huge, and we basically were able to see that we still have the water quality we were looking for, and may even be able to reduce the ammonia addition that we're adding for chloramination. And I don't know if Michelle or Phil. Michelle can answer a bigger question of how she sees this being maybe applied nationwide.
Yeah, maybe this winter we should look at how well it performs seasonally in the lower wastewater temperatures.
And for what it's worth, we, as part of this project, started a national survey. Some of you may have seen some of those results in the past. We have facilities across the country, from east to west coast, from Texas to Minnesota, in terms of geographic variation. And there are facilities across the country that are doing this. They might have, again, slightly different approaches. Natalie Beach talked about this a bit in webcast too. They might write in seasonal low DO versus all year round. But I do see low DO as a kind of, in my opinion, assuming you can justify, you have the turn down on your blowers and all that other stuff, it seems like a no-brainer. You should be doing it. Come on,
and then I'll answer the question that you originally asked, which is, we plan on putting a hydrocyclone at this plant in the next few months. And so stay tuned. We should have some good data, hopefully, with that also.
Great. Well, I think we're at time. And so with that, I think we'll stop there. This concludes our webcast. Thank you all for participating. Special thanks to our speakers today, Michelle and Tom and Phil. And since this also concludes our three-part webcast series on this topic, thanks again to our speakers from Webcast 1, Tanya Rausch-Williams and Daniel Noguera, as well as Webcast 2, Natalie Beach, Steve Kestel, and Alex Exter. All three webcasts will be available for viewing on demand on the WRRF website if you missed any of those along the way, or if you want to rewatch any portions of the webcast. So thank you again for participating, and I hope everybody has a great day.